Okay, so I introduced the concept of ripple carry adders a couple of videos ago and talked in the last short video a little bit about one of the problems with the ripple carry adder, and that is that it executes very slowly. Decided that to move information through each stage of a ripple carry adder is going to take about 1 nanosecond per stage, and so for a 32-bit adder, it's going to take about 32 nanoseconds to form a complete answer, allowing enough time for the carry information to ripple all the way through all stages. And that means that a ripple carry adder can only operate at about 33 megahertz, best case. So if we want to have an adder that can operate faster, we have to break that ripple carry chain. So if I sketched a couple of bit slices like so, and into this bit slice come the operands A0 and B0, and I'm trying to decide what the carry in to the next stage might be here. We can think about forming this carry in terms of the information we have available in the lower significant bits. This carry in to this stage will be driven anytime these bits are both a 1. So if A0 and B0 are 1, we'd add 1 and 1 together and get a 2. The sum bit out would be a 0, and the carry out to the next stage would be a 1. That sort of makes sense. Let's see if we can generalize that to maybe the carry into the next stage. So this would be the A1 and B1 stage, A2 and B2. And if we ask the question, when might this carry in be driven? Well, following the reasoning we just came up with, if A1 and B1 are both a 1, we know this carry in is going to have to be a 1. If A1 and B1 are both a 0, we'd know that this carry-in would be a 0, right? If you did a couple of examples here, for instance, if let's see, A2 and B2, if I had these two numbers, doesn't matter what the other bits are, and I'm looking at the carry into this stage right here. I know in this example, adding a 0 and a 0 is going to give me a 0 with a carry out of 0. I also know if I was looking at this sort of pattern, and again I'm looking at this bit stage here, because the previous two bits are both 1, I know the carry into this stage is going to be a 1. So if the previous bits are both a 1 or both a 0, I know what the carry into the following stage is going to be. But what if one of the bits is a 1 and the other one's a 0? In that case, the next least significant two bits don't by themselves determine what the carry into the next stage is going to be. Instead, I'd have to look further down the chain. If the two next door bits, if the two less significant bits are a 1, 0, or 0, 1, in other words, if the XOR of these two bits is a 1, then the carry in isn't determined by these two bits, but instead by information further down the chain, and this stage is simply going to propagate information. So based on this discussion, I can kind of come up with a couple of new terms. If two bits coming in, two operand bits coming into a given stage are both 1, I'm going to generate a carry out into the next stage. If they're both a 0, there's going to be no carry out generated. But if they're a 0, 1 or a 1, 0, then I'm not going to generate a carry, but I'm going to propagate information from an earlier stage. And therefore I can come up with a new bit slice that would build that in. So my new bit slice then is going to have the same two operand bits coming in, A n and B n, and I'm going to generate a sum out. But now I'm going to generate two other signals. I'm going to call those signals G for generate and P for propagate. The generate is going to be used by the next stage to generate a carry whenever these two bits are both 1. And so the generate signal is going to be the AND of these two bits. And the propagate signal is going to simply propagate a carry from an earlier stage. So I'll show a carry in here. If these two bits are 0, 1 or 1, 0, I'm not going to generate a carry, but I'm going to propagate carry information from an earlier stage. So with that information, then I can come up with a new bit slice circuit for a reconceived adder. And that bit slice circuit is going to have bit slices just like the ripple carry adder, but the bit slices are going to have slightly different functions. Each bit slice is going to bring in the two operand bits, and each bit slice is going to produce a sum bit, a propagate, and a generate output. And then I can build identical ones of these, identical bit slices, and again connect n of them together to produce an n-bit adder that doesn't suffer from the need to propagate a carry through each stage. I will illustrate that. All right, let's just draw, well, I'll draw 4 stages to start with. One more stage here. A, B. So those are just 4 bit slices of maybe an n-bit bit slice adder. And I'm going to connect A0 and B0 here, A1 and B1 here, A2 and B2 here, and A3 and B3 here, and so on. I'm just going to show the first 4 stages though. Okay, I'm going to assume, well, let me show that each stage is also going to have a carry in because I need a carry in to each stage, but instead of a carry out, I have the propagate and generate signals. All right, into the 0th stage, I'm going to assume that this carry in comes from the outside world, and I'm just going to say carry in up here. So that carry in could be used if I wanted to tie this adder together with another adder just like it. I could chain the carry out from the most significant bit of another module to the carry in of this. Or if it's just going to be an n-bit adder, I would just tie carry in to ground. But for now, I'm just going to show it as a generic carry in. So I know that this carry in, based on our discussion, is going to be driven to a 1 if I generate a carry from the previous stage. So I'm going to show an OR gate there. So now if this is a 1 and this is a 1, I'm going to drive generate to a 1, and that's going to drive a carry in. Or, based on our discussion, if that's a 0 and that's a 1, or that's a 1 and that's a 0, in other words, if the XOR of those two bits is true, I'm going to propagate a carry. So I'm going to show propagate coming down, and in this case, I would propagate a carry from the outside world. So I'm generating this carry in now without rippling information through that full adder. I'm sort of bypassing it. In the same fashion then, this carry in is going to be driven if I generate a carry from this stage, right? Because if that's a 1 and that's a 1, I know I'm going to drive a carry into the next stage. Or if that's a 1 and that's a 0, or that's a 0 and that's a 1, I'm going to propagate a carry from the previous stage, and that carry would arise if I generated a carry in that stage. So this says now if that's a 1 and that's a 1, I'm going to generate a carry, And if that's a 0 and a 1 or a 1 and a 0, I'm going to propagate that into this carry in. Or if I'm going to propagate a carry from here and propagate a carry from here, and I had a carry in generated all the way out here. So that circuit's getting a little bit bigger, but let's just slow down and think about it for a second. All this is saying is I'm going to generate a carry into the A2, B2 bit stage, the second bit stage. If I generate a carry in this stage, or if I propagate a carry from this stage and I generate it in this stage, that's that gate there, or if I propagated it here, and generated it here. In that case, I'll also generate a carry there. Well, now we've kind of got a pattern going. Into this stage, I'm going to have a carry in if I generate it in this stage. Right? If that's a 1 and that's a 1, I'm going to generate a carry right into the next door neighbor. Or if that's a 1 and that's a 0, that's a 0 and that's a 1, I'm going to propagate a carry. And if I had generated one in this stage, I'm going to propagate that into this carry. Or if I propagate a carry in this stage, and I propagate a carry in this stage, and I generated it in this stage, I'm going to have a carry into that stage. Lastly, if I propagate a carry in this stage, I propagate a carry in this stage, I propagate a carry in this stage, and I generate a carry all the way out here, I'm going to drive a carry into that stage. Now, I drew this picture much more neatly in the class readings, so you can look at it there. But the idea is for any carry in, for any stage, for any carry in downstream, I'm going to drive the carry in. If the next door neighbor, if its 2 bits were both a 1, I'm going to generate a carry in. Or if the next door neighbor was a 0 and a 1 or a 1 or a 0, I'm going to propagate a carry. And then if I propagate it here and generated it there, one stage earlier, I'm going to have a carry in. Or if I propagate here, and generate here, I'm going to have a carry in. Or propagate here, and generate here, I'm going to have a carry in. And so forth. Okay, so that means then we need to have a new bit slice module. So in that bit slice, it's going to look a little bit like our previous bit slice. The sum bit will be formed in exactly the same way. I'm going to have XOR gates combining A, B, and carry in to produce the sum. But now I'm not generating a carry out. There's no carry out in these bit slices. Instead, I'm going to generate the propagate signal, and I've already got that. A XOR B is propagate. And I'm also going to create a generate signal, which is just the AND of A and B. So if I put that circuit in a box, now I've got a new bit slice. This bit slice is different than the bit slice circuit I used for the ripple carry adder because it does not generate a carry out. It generates generate and propagate instead. And now this new bit slice circuit could be used in a combined circuit that kind of looks like this. I'd have bit slice stages. I'll draw 4 of them that each have an A and B input for the operand bits. They each generate a sum output. They each have a carry-in input. But instead of a carry-out output, they both generate the generate and propagate signals. Now this circuit can't live all by itself with just the bit slices. We also need to combine all of these gates into this circuit. So down here I'm going to draw another circuit, and I'm going to call this circuit the carry propagate / generate network. And the propagate generate network is going to contain all these circuits here. So the propagate and generate from each bit slice is going to go into this network. And out of this network are going to come the carry-ins to the subsequent stages. And then the sum bits are just going to kind of bypass and go right through. So I'd have, if this is A0, B0, A1, B1, A2, B2, A3, B3, I'll have sum 0, sum 1, sum 2, sum 3, and so on. So these bit slices develop the sum bits directly, but then the the generate and propagate signals are fed into this network, and this network then generates each carry out, or each carry in, I should say, to each bit slice simultaneously. So note this signal here, the carry in to the third bit slice. If this were a ripple carry adder, then to generate the carry in to that bit slice, I would have had to have propagated through this and this and this bit slice, each one taking about a nanosecond, each one having 3 gates I'd have to move the signals through, so 9 gates total. But look here, this carry into this stage only goes through at most 2 gates. It'll go through that gate and one of these, depending on the generate and propagate signals from the earlier stages. So every single carry can be formed with just 2 gate delays anywhere in the entire adder. Just 2 gate delays. And because I can generate any carry with just 2 gate delays, that means no matter how big the adder gets, however many bits long it is, I can still form an answer with just 2 gate delays. And so this circuit can run a whole lot faster than the ripple carry adder. So we have a name for this circuit as well. If I put all of this in a box like this, and so just the operand inputs and the operand outputs are exposed outside the box along with the carry in, I would call that then a carry-lookahead adder. The carry-lookahead adder has more gates. We had to add a whole bunch of functions, a whole bunch of transistors to the circuit, so we made a bigger circuit, but it runs a lot faster than the ripple carry adder. So by rethinking the addition problem, we eliminated the bottleneck of the ripple carry adder. Remember, here in the ripple carry adder, we had to wait for the carry information to get rippled through each stage. By rethinking that process, we were able to come up with a way to generate the carry-ins to each stage more efficiently and more quickly, and therefore make the adder run a lot faster. And that's a fairly typical thing. We'll see that again down the road a little bit, that the first design we come up with might be conceptually the simplest design, but it might not be the fastest or the best one. So pretty typical to rethink a design, add some more engineering, and come up with a better and faster solution. Okay, that's it for this video. I will talk to you next time.